And the third example for today deals with designing a can. We did an example like this yesterday, and they even mentioned example 2, and they're just making a slight change to it. This is a little bit more realistic approach to the problem. So in making a cylinder, we have to make the side and the top and the bottom. Fortunately, the side, if you cut down the middle of a can and you roll it out, you have a rectangle. But in cutting out circles, and you can imagine doing this with a sheet of paper, you're going to have scraps from the circles. And so what they're imagining in this situation, I'll show you on the next page here. So this is what a cylinder would look like if you were to break it down into its component pieces and flatten it out. And what they're imagining is that this circle comes from a square piece of tin, and so this is what it would look like. This is the scrap that we have left over. So yesterday when we did this problem, we wanted to minimize the surface area, and we were thinking about this surface area, which is pi r squared plus pi r squared, or 2 pi r squared, plus 2 pi r h. Today when we consider the problem, we're going to take into consideration, instead of just pi r squared, we're going to do the whole square, because you can't reuse this scrap. And so, this is a circle, and this is 1r, one radius. This is another r. So each side of the square is 2r, and so the area for each one of these squares is 4r squared. So, again, we'll start with the fixed. We absolutely know that the volume is going to be 1 liter, or 1,000 cubic centimeters. And we remember, hopefully from yesterday, that the area of a cylinder is pi r squared h. What we've just discovered here is that the surface area today is not going to be 2 pi r squared plus 2 pi r h, but 8r squared plus pi r h. And we're going to see how that affects the change. Now, hopefully you'll recognize this is a problem. We do not like our functions in 2 variables. So we need to replace the h with something in terms of r. So we're going to go back to our volume equation. Again, this one's fixed. And so if I divide by pi r squared, that should tell me what h is equal to. Okay, and now we're going to plug this value of h into this variable right here, and that should get us, that's what we've done here. That's going to get us the area function just as a function of r, not as r and h. The pi's cancel. R over r leaves 1 r on the bottom. This is good as far as plugging things in, but if I'm going to take the derivative, I should probably write that as r to the -1 so I can use the power rule instead of the quotient rule. And then finally, we know that we're going to have to take the derivative here, 16r to the 1, and then negative 2,000 r to the -2. We're going to drop that power by 1. And again, if I'm going to plug stuff in, I'd rather work with the r on the bottom instead of looking at that. Now, if I'm going to take the second derivative, I'm definitely going to look at this. But these are equivalent, so we'll change it for our purposes. Now that we have the derivative, we need to find the endpoints and the critical points. Hopefully, just by thinking about this, we know that the radius of the can has to be greater than 0. If the radius is 0, it will not have any volume. Okay, so we're just going to make note of that. And as far as the critical points, they occur when the derivative, this is how I've written the derivative, when the derivative doesn't exist. It's the first option. And if you look at this, you can't mess up 16r, but you can mess this up if you plug in an r squared, if you plug in a 0 on the bottom. If you let the bottom equal 0, that means r is 0. Now, if you'll remember, we just said that the radius has to be greater than 0, so this doesn't really matter. Okay, and then we also need to consider the other possibility is that the derivative is equal to 0. And so I'm literally just going to take this thing and set it equal to 0. That's what I have in the first equation. I don't like the r squared on the bottom, so everybody gets multiplied by r squared. First term becomes 16r cubed, just 2,000, and 0 is still 0. I'm going to add 2,000, divide by 16. So that tells me that r cubed is 125. Take the cube root, and fortunately, in this situation, r is a perfectly good integer. No rounding required, and we can all move about our business. Okay, so we've got just 2 points to test. One is 0 and one is 5. And again, technically, we shouldn't even have to look at r equals 0 because we know that wouldn't make any sense. But just for kicks and giggles, I'm going to plug it in. So we're going to test these 2 points. The first one, sure enough, we get something that's undefined. So not surprising there. And then if we plug in 5, we get, again, a nice number, no rounding required, and 600. And that seems to make sense. We were asked to minimize the amount of aluminum that we use, which is measured in area or surface area. And so presumably the answer is 600, but I just need to know, is this a maximum or minimum? One way to tell that would be to take the second derivative, because that's going to tell us concavity. And so if you look back at the first derivative on this page, if you take the derivative of that to get the second derivative, you'll see it's this. Now, 16 is always positive, 4,000 is always positive, and if you plug in an r that's greater than 0, r cubed is always positive. And so if you got a positive number plus a positive number, so the second derivative is always positive, which is to say it's always concave up, right? The function's always concave up, and therefore, if you just imagine, I'm tracing a concave up, right? If the derivative is 0 and it's concave up, you have to have a minimum, which is good. That's what we wanted to do. We wanted to minimize the amount of aluminum that we used. So that was 600 from the previous page. We got that by plugging in a radius of 5. And to find the height of the can, we should just plug it back into, again, I'll remind you, at the very beginning, we found what h was equal to in terms of r. And so we're just going to plug that in and get a nice approximation there. And that's the problem.